Recently, we spent a lot of time talking about Taylor series, and that was built upon the idea of using sums of powers of x to approximate a function. Today, we're going to talk about Fourier series, where we're still going to try to approximate functions, but instead of using power functions as our kind of building blocks, we're going to focus on trig functions. The other thing we haven't addressed so far is the possibility that in trying to approximate a function, we might not even be able to find its Taylor series. All of our examples up to this point have been nice functions where finding the Taylor series was appropriate, and we saw different things we could do with that. But consider this function f of x that I have graphed here, and we can think about putting our focus on different x values. So for one, we could think about a few things. So why can we not find the Taylor series for this function f of x that I've plotted here, centered at x equals 0? So thinking about what we would need in order to do that, if I'm trying to find the Taylor series centered at 0, I need to be able to find infinitely many derivatives of the given function at the value 0. So we can certainly find f of 0. It appears that that is pi over 2. But as soon as I start to try to find even the first derivative of f at 0, that's not going to be possible, right? The function isn't even continuous there. So likewise, I wouldn't be able to find the second derivative, the third, and so on. So one of our underlying assumptions is that our function f has to be differentiable at the point, the center value. And then beyond that, I can change my center, and I can find the Taylor series at other points. So I'll point out that the Taylor series centered at x equals, let's say, positive pi over 2 is the function, or it's just pi over 2. I'll point out that you can find, again, that would lead me to focusing on the graph here, and the value of the function there is pi over 2. And the derivatives are defined there. It's just that the first derivative and any higher order derivatives are all 0. So the Taylor series would just yield a constant. So that would be a great approximation of the function on that interval from 0 to pi. But as soon as I move away from that, then all of a sudden it's not a good approximation. It's very far off from the actual value of the function. And likewise, if we were to find the Taylor series at a different value of x, say centered at minus pi over 2, then yet again we could find this Taylor series, and it would end up evaluating to the value of the function there, because once again all higher order derivatives would be 0. And so we get a different constant here. And again, that would be a good approximation close to x equals minus pi over 2. But if I veer too far away from it, it's not going to be a great approximation. So we're going to see that these Taylor series, when we're using these as approximations of our function, they're good local approximations. And that's a reflection of the fact that we always indicate the center and then the interval of convergence, where, of course, unless the interval is the whole real line, we're usually focused on a cluster of x values very close to the center. So thinking about this function, where we've now seen a few problems with Taylor series as I move the center around, there's another feature of this function that's going to make it very well suited to a Fourier series approximation. And that's the idea that this function is what we call periodic. So often we are familiar with the term periodic when we're talking about trig functions, but just to give it a full definition here, a function f of x is k periodic, or we might say that it has period k, if f of x plus k is equal to f of x for all x. And classic examples of periodic functions are, say, sine of x, cosine of x. Those have period 2 pi. And with a graph, you can really visualize the periodic property because we can see this behavior in which it's repeating itself over a full period. So the larger goal in mind when we're talking about Fourier series is that we want to try to approximate periodic functions using not powers of x, but sines and cosines. So, of course, one important feature is that, as I noted before, sine and cosine are periodic functions. And in particular, we're going to rely on a fact. We will use the fact that 2 pi periodic functions can be written as a sum of sines and cosines. So I'll point out that I referenced 2 pi periodic. In this course, we are only going to look at the notion of using Fourier series to approximate 2 pi periodic functions. But I do want to point out that this is a much broader topic, and they're also useful for approximating functions of general period. So we're just not going to get into that in this particular semester. So now we're ready with this kind of underlying fact to define Fourier series. So we're going to assume that f is 2 pi periodic. So let f of x be a 2 pi periodic function. Then the Fourier series of or for the function f of x is the following sum. A sub 0 plus the sum from k equals 1 to infinity of a sub k cosine k of x, kx I should say, plus the sum from k equals 1 to infinity of b sub k times sine kx. Now, one thing I should point out here is that there are some coefficients involved, right? There are these coefficients. And what we need to do is define how those coefficients relate to f of x. Just for a comparison, I'll point out it's similar to how we started with the idea of a power series. A power series, we said, had general form c sub k x minus a to the k. And once we talked about a Fourier series, a Taylor series, we said that we could in particular define that coefficient as the kth derivative of our function f evaluated at a over k factorial. So we got this connection between our Taylor series approximations and these coefficients being dependent on derivatives of f. Consequently, we started to see if we had the Taylor series, we could use that to give us information about the derivatives of f. What we'll see here is that, yet again, these coefficients, of course, depend on my function f of x, but rather than depending on derivatives, they actually are going to be related to integrals. So let me define these here. We will consider where these coefficients come from in a later video. So right now, we're just going to treat them as fact, and we'll get used to applying these formulas. But at the moment, it's not supposed to be clear where these formulas come from. So as it turns out, the constant term a sub 0 is 1 over 2 pi, the integral of f of x. Notice that's the average value of the function f over the interval from minus pi to pi. The a sub k, which played the role of the coefficient of the cosine function, is 1 over pi, the integral from minus pi to pi, of f of x times cosine kx. So the a sub k both sits in front of cosine in the summation, and you can see that we also find it by integrating f times that same cosine function. And then finally, b sub k is somewhat symmetric to that. We have the integral from minus pi to pi of f of x times sine kx. And again, b sub k is the coefficient associated to sine kx, and we find it by integrating f times that same sine function. So a few more things I want to point out. Notice that unlike Taylor series, there's no longer a notion of a center. And in fact, we're going to see that these approximations are what we call global. So they are pretty much representative of the function in almost its entirety. We'll point out an idea where we have to look at continuity. And then the other thing that might be a little confusing, when we talked about Taylor series and power series, we always started at k equals 0. And of course, if you look at my Fourier series representation, I've intentionally started these at k equals 1. And one thing I want to point out so that that's clear why we have that, a few things. If I were to start at k equals 0, then one thing that would happen is in that second summation, sine of 0x, sine of 0, that would be 0. So starting that second summation at 0 would be pointless because the 0th term would be 0. Now, cosine of 0 is 1, so you could get a constant term from the first sum, one that's not attached to a trig function, but we already account for that with the a sub 0. So that's really the reason we can start these at 1. So you just want to be a little bit careful since we've been so used to starting our Taylor series at k equals 0.